Gears turning force. Introduction. A gear is a type of machine. Most gears are a rotating circle with little teeth around their circumference. When two gears are turning side by side, this is called meshing. The gear where the turning starts is called the driver gear. It drives the follower gear. Gears can change the direction of something turning, change the speed, or multiply the turning force or torque. When gears are multiplying turning force, this is called mechanical advantage. Gears increase torque when a smaller gear drives a larger gear. The gear ratio measures the size different. We calculate the gear ratio by dividing the driver gear's number of teeth by the number of teeth on the follower gear. Gears have been used for millennia. Archimedes used gears in designing machines. The earliest surviving example is Zinskai's theory of mechanism, Figure 1. It was found in 1901 in a Greek shipwreck. It had 29 gears and it was made in approximately 82 BC. It was used to predict the motion of the moon and planets and was called an ancient computer. Other early uses for gears include water wheels, threshers, and clocks. Figure 2 shows one of the sketches in Leonardo da Vinci's notebook of a machine with gears. Modern gear usage includes spikes, Figure 3, cars, watches, and escalators, Figure 4. Experiment. For my experiment, I built a model crane to lift up a test weight, 199 grams. In different experiments, we tested different pairs of different sizes of gears. Table 1. Table 2 shows our setup of how many teeth were on the driver gear and follower gear. I tested which gear pairs were quickest and which were more difficult. I counted the number of turns it took to raise the weight to a test height, 30 centimeters. I also measured how much force it took to lift the weight in one experiment compared to others. Results. I did 7 experiments with my crane. Table 3, and experiment number 3 was the easiest and took the most number of turns. This is because that gear ratio was the smallest. Experiment number 5 was very hard, but took the least number of turns. This is because this gear ratio was the largest. This is the crane we used for experiment number 3. The gear ratio is 0.2. It's easy to turn, but it took 80 turns to lift up 30 centimeters. This is the crane we used for experiment number 5. The gear ratio is 5. It's very hard to turn, but it spins very fast. Conclusion. In conclusion, I found out that if the gear ratio is large, it's very hard to turn but takes the least amount of turns to raise the weight to the test height. If the gear ratio is small, it's the easiest to turn but takes the most turns.